Welcome to episode 17, and in this episode we'll present a detailed design for an interrupt controller for our 6809 system. We'll start by listing our desired features. Next, we'll go through a design which supports the planned features. We'll develop a prototype interrupt controller circuit on a breadboard, and then test and validate the prototype, including making some initial software changes to the monitor program to support interrupts. Let's get started. Here are our desired features for the interrupt controller. We will support 7 individual hardware interrupt request inputs, all of which will share the CPU's level-triggered IRQ input. 5 of the interrupt request inputs will be level-triggered, and 2 will be edge-triggered. The individual interrupt requests will be prioritized, and the interrupt controller will have a mechanism to report the identity of the highest priority interrupt to the CPU. The interrupt controller will also have a mechanism to allow individual hardware interrupts to be masked and unmasked. Here is a schematic of a design which implements the desired features. The interrupt controller circuit is somewhat complex and is split into several components. The components are inputs and edge detection, the mask register, the mask-unmask logic, the priority encoder, and the CPU IRQ Signal Generator. Let's start by discussing the inputs and edge detection logic. There are 7 interrupt request inputs with signal names IRQ1 through IRQ7. These are the inputs which external devices can use to generate a hardware interrupt. IRQ3 and IRQ6 are edge-triggered interrupts, meaning that a transition from a low voltage to a high voltage indicates that an interrupt condition has occurred. The other interrupt request inputs are level-triggered, meaning that a low voltage is asserted continuously to indicate that the interrupt condition exists until the CPU's interrupt handler routine services the interrupt and clears the condition that caused the interrupt to be requested. Because it will not necessarily be the case that all of the interrupt request inputs will be actively driven by a hardware device, pull-up and pull-down resistors are used to ensure that the inputs are in a known, non-asserted state when not actively driven. The level-triggered IRQ inputs do not require any special processing and are forwarded directly to the IRQ EnableDisable logic. The edge-triggered IRQ inputs cannot be sent directly to the EnableDisable logic. Instead, they are fed to the clock inputs of 2 D-type flip-flops in a 74HCT74 device. The 2 D-type flip-flops normally output a high voltage, which corresponds to the interrupt not being asserted. When a positive edge arrives on the clock input, the output latches a low voltage which is continuously present on the flip-flop's D input. This causes the corresponding flip-flop output to send a low voltage to the EnableDisable logic. When the software interrupt handler has handled the condition signaled by an edge-triggered interrupt, it asserts the set input on the appropriate flip-flop using the IRQ3 clear or IRQ6 clear signals. These cause the output of the appropriate flip-flop to return to generating a high, non-asserted voltage. Next, let's discuss the mask register. The purpose of the mask register is to allow each hardware interrupt input to be selectively enabled and disabled. The register is a 74HCT574 octal D-type flip-flop. The outputs Q1 through Q7 are the mask signals for the interrupt request inputs IRQ1 through IRQ7. When a mask signal is 1, meaning a high voltage, it masks its corresponding interrupt request input, preventing it from being forwarded to the CPU and triggering an interrupt. When a mask signal is 0, the corresponding interrupt request is forwarded to the CPU, allowing it to occur normally. The mask register is a memory-mapped I/O device, and the CPU can control the mask register outputs by writing a byte to the register. The data bus signals D1 through D7 are connected to the inputs of the mask register, and the mask register's clock input is driven by an OR gate which combines the memory write signal with the interrupt controller's chip select signal. If either the memory write signal or the chip select signal are high, meaning that they are not asserted, then the output of the OR gate will be high. In this state, the mask register ignores the values on the data bus. When both the memory write signal and chip select signal are low, meaning that they are asserted, the output of the OR gate will be low. When either the memory write signal or chip select signal becomes high again, which will occur at the end of the bus transaction that writes a byte to the register, A low to high transition on the OR gate's output will clock the data value on the data bus into the mask register. The mask register's outputs will now be identical to the data values written to the register. Next, let's talk about the EnableDisable logic. The purpose of the EnableDisable logic is simple. Allow unmasked interrupt request signals to trigger a CPU interrupt and prevent masked interrupt request signals from triggering a CPU interrupt. The EnableDisable logic consists of 7 OR gates in two 748CT32 devices. In each OR gate, one input comes from the interrupt input and edge detection logic, and one input comes from the mask register. Let's consider the case of the OR gate handling the IRQ1 signal. If the input generated by bit 1 of the mask register is a high voltage, then the output of the OR gate will be high unconditionally. This means that an interrupt request coming from an external device on the IRQ1 input will simply be ignored and will not be forwarded to the CPU. Thus, IRQ1 is disabled. If the input generated by bit 1 of the mask register is a low voltage, then the output of the OR gate will follow the IRQ1 input. This means that if IRQ1 is high, meaning not asserted, then the OR gate output will be high. If IRQ1 is low, meaning asserted, then the OR gate output will be low, so IRQ1 is enabled. Because each interrupt request has its own OR gate controlled by a dedicated bit in the mask register, each interrupt request can be individually enabled or disabled. Next, let's discuss the priority encoder. Because all 7 hardware interrupt request inputs share the same CPU IRQ input, it will be useful for the interrupt controller to provide a mechanism for the software interrupt handler routine to determine which interrupt request should be serviced next. Because more than one interrupt request could be asserted at the same time, the interrupt controller prioritizes the interrupt requests, with higher numbered interrupt request inputs having priority over lower numbered interrupt request inputs. For example, if IRQ7 and IRQ3 are asserted at the same time, the interrupt controller should indicate that IRQ7 should be handled next. To prioritize the currently asserted interrupt requests, we use a 748CT147 10-to-1 priority encoder device. If any of the priority encoder's 9 inputs are asserted by being driven low, the outputs will generate the binary representation of the highest priority input. For example, in the case of IRQ7 and IRQ3 being asserted simultaneously, the outputs of the priority encoder will generate the binary representation of the integer 7. If none of the inputs of the 748CT147 are asserted, then its outputs will generate the binary representation of the integer 0. One peculiarity of the 748CT147 is that the outputs are inverted, so that when the binary representation of 7 is generated, instead of generating the bit pattern 0111, as would normally be the case, the outputs instead generate the bit pattern 1000. Another problem we must solve in allowing the CPU to read the value of the priority encoder is that the 748CT147's outputs are always actively driven. We cannot connect them directly to the data bus lines because they would interfere with other devices using the bus. Fortunately, both of our problems, the problem of the inverted outputs and the problem of driving the data bus only when requested by the CPU, can be solved with a single device, the 748CT540 octal inverting buffer. Because it is an inverting buffer, when the 748CT540 propagates the values of its inputs to its outputs, it inverts each input. So if the priority encoder is outputting the inverted value 1000 to indicate that the IRQ7 input is being asserted, the 748CT540 will translate this value back to the non-inverted value of 0111. In addition, by driving the 748CT540's G1 and G2 inputs with the memory read signal and the interrupt controller's chip select signal, the outputs of the buffer are only actively driven when the CPU has explicitly requested to read the current interrupt priority value. If either the memory read signal or the chip select signal is not asserted, then the buffer's outputs will be tri-stated and thus will not interfere with any other device that is using the data bus. Finally, let's talk about the IRQ Signal Generator. The purpose of the IRQ Signal Generator is to assert the CPU's IRQ input whenever any of the interrupt request signals generated by the EnableDisable logic are asserted. This is accomplished by combining the three input AND gates in a 748CT11 device into what is effectively a 7-input AND gate. The output of an AND gate is high if and only if all of its inputs are high. So, when all of the interrupt request signals are high, meaning not asserted, the output to the CPU's IRQ input is high, and no CPU interrupt is generated. If at least one interrupt request signal is low, meaning asserted, that is sufficient to drive the CPU's IRQ input low, causing a CPU interrupt to be generated and resulting in the execution of the software interrupt handler routine. Alright, I have built the interrupt controller circuit on the breadboard. So here is the mask register. These two 748CT32 devices are the EnableDisable logic. This is the 748CT147 priority encoder. This is the 748CT11 that contains the AND gates that do the IRQ generation. This is the 748CT74 that contains the two D-type flip-flops that do the edge detection. And this is the 74HCT540 that inverts the outputs from the priority encoder and also buffers them for access to the data bus. And I have used my multimeter to do continuity testing to test all of the connections against the schematic, and I have double-checked them, and everything seems good, so I think we are ready to test this with the actual system. Alright, before we test the interrupt controller hardware, it would be a good idea to make sure that the 6809 system still works. So I have the USB serial adapter hooked up to a USB port. I have the system powered on. I have QtCom, the serial terminal program, opened. So let's open the USB serial device. Okay, that looks like it worked. So let's reset and see if we get a prompt, and we do. So that looks promising. And let's load the test program. Let's see, so that is testprog.ihx. Actually, before we do that, we need to send the D command for download to the monitor program. So let's load the data for the test program. Okay, okay, that's promising. So that should now be loaded to address 1000 hex. So let's change the monitor address to 1000 hex. And then if we do X, what we should see is that this is the count program that's going to display an increasing count on the hex display here, which is just outputting increasing binary values on port A of our 82C55A device. All right, let's see if that works. So we should see this count up, and it does. Okay, so that's quite promising. That does suggest that the system is still working. All right, let's try to connect the interrupt controller. Alright, so we've made all of the requisite connections from the main system to the interrupt controller. We've connected the memory read, memory write signals. The IODEV3 signal, which is generated by the address decoding logic, has been fed to become the chip select for the interrupt controller, allowing us to read from the priority encoder and also write to the mask register. The timer 1 output from the 82C54 has been connected to the IRQ3 signal, which is one of the edge-triggered interrupt inputs that the interrupt controller supports. The PC0 and PC1 signals from the 82C55A are being used to drive the IRQ3 clear and IRQ6 clear inputs to essentially allow us to reset the flip-flops that do the edge detection. And finally, the IRQ out output from the interrupt controller has been connected to the CPU's IRQ input. And I believe everything is connected correctly. I have a multimeter set up in current measuring mode in series with the power supply because I would like to see how much current the circuit is drawing. If there's a short circuit, it should be obvious by looking at the output. All right, I think we're ready to power it on. Alright, so here is the moment of truth. I am powering on the power supply. Okay, this is an excellent sign. We're seeing the prompt from the monitor program. Oh, let me get the multimeter on here. So we're drawing about a little over 200 milliamps. I think that's reasonable given everything that's connected here because we do have this hex display hooked up. All right, I'm going to try the same experiment as before, so let's try to download our test program. All right, so that is testprog.ihx. Okay, that looks promising. We'll set the monitor address as before and execute it. And there we go. We're getting the counts counting up on port A of the 82C55A. So this is excellent. This is an excellent result because even though we're not actually doing anything with interrupts or the interrupt controller yet, the circuit does not cause any problems for the system. All right, I think we are ready to try some actual interrupt handling. We're going to need to make some software changes, so that will be our next task. Let's discuss the software changes to the monitor program needed to support interrupts. I will discuss the changes at a high level, but you can read the source code on the GitHub site for full details. The IODEV3 signal is used as the chip select for the interrupt controller. This means that the mask register and IRQ priority are mapped at address hex 8060. Writing a byte at this address sets the mask register value. Reading a byte from this address gets the numeric value of the highest priority IRQ currently being asserted. The IRQ CTRL init function, which is called from the monitor entry point code, is responsible for initializing the interrupt controller hardware and setting up the software data structures that will be used to handle interrupts. It sets the initial mask register value, which disables all IRQ inputs by default. Note that a memory variable called vmaskreg maintains a copy of the mask register value since there is no way to read the contents of the mask register. It also resets the flip-flops used for detecting edge-triggered interrupts to ensure that they are outputting a high, non-asserted voltage. IRQ CTRL init also copies the default handler functions for each of the 7 external interrupts into a table called VIRQ tab located in RAM. By changing the entries in this table, we can install custom handler routines for any of the 7 supported external interrupts. The IRQ dispatch routine is the main IRQ handler routine called automatically by the CPU when its IRQ input is asserted. It reads the interrupt priority from the interrupt controller's priority encoder. If the priority is not 0, it loads the address of a subroutine from VIRQ tab and calls the subroutine. When the subroutine returns, it uses the RTI instruction to return control back to the main program. Note that we store the address of IRQ dispatch in memory at address FFF8, which is where the CPU looks for the address of the IRQ interrupt handler routine. 2 new commands are added to the monitor. The M command allows the mask register value to be set. This allows us to selectively enable and disable specific external interrupts. The Q command toggles bit 4 of the condition code register to allow IRQ interrupts to be enabled and disabled at the processor level. When the 6809 CPU resets, bit 4 of the condition code register is set to 1, which means that the CPU's IRQ input is ignored. By setting this bit to 0, the CPU will dispatch to the software IRQ handler routine when the IRQ input is asserted. By setting this bit back to 1, the IRQ input will again be ignored. Now that we've made the required changes to the monitor program, we can develop a test program to see if the interrupt hardware and software works correctly. This program is inttest.asm and is designed to be compiled into an Intel hex file and loaded into RAM by the monitor program. The test program will store an integer count value in a variable in RAM. It will be loaded into RAM at address hex 1000, which is its entry point. When the entry point is invoked as a subroutine, it will patch a custom function, IRQ3 handler, into entry 3 of the VIRQ table. This will establish the IRQ3 handler routine as the handler for IRQ3, which is the periodic timer interrupt generated by Unit 1 of the 82C54 timer counter device. This is an edge-triggered interrupt generated about 14 times per second. The handler function writes the current count to port A of the 82C55A and then increments the counter. Before returning, it calls the monitor's reset IRQFF function to reset the IRQ3 flip-flop. If we didn't call this reset function, then IRQ3 would continue to be asserted. The behavior we expect to see from executing the test program's entry point function is that once IRQ3 is unmasked and interrupts are enabled at the processor level, we should see increasing count values being output on port A. Alright, so let's see if we can get things working here. So let me power on the 6809 system and then reset. And then let's open our USB serial device. Let's reset again so we get a prompt. Okay, so basically what I want to do here is load our test program. So that's inttest.ihx. We need to do the D command for download first, so let's do that. All right, so this loads the test program into memory, so that looks successful. So if we run the test program, so let's go set the monitor address to hex 1000, and then the S command invokes the current address as a subroutine, so that will call the entry point of the test program. And so in theory, what has happened is that the VIRQ tab table of IRQ handler routines has now been patched so that IRQ3, when it is received, now calls the test IRQ3 handler in the test program. All right, so at this point, nothing is happening because the mask register is set to hex FF, so every interrupt is basically blocked by the mask register, and also the CPU condition code register bit 4 is set to 1 so that the IRQ input on the CPU is also being ignored currently. All right, so let's change the mask register value to F7, so that will set bit 3 corresponding to IRQ3 in the mask register to 0, allowing IRQ3 to be generated. Okay, so that looks like it worked. And now the Q command in the monitor will basically clear bit 4 in the condition code register, which should allow IRQs to be handled. And what we should see is that on the hex display here, we should see the count values now increasing. So let's do the Q command, and there it goes. So these count values are being generated by the interrupt handler. And what's really cool about this is that because this is a process that is being handled by interrupts, the monitor continues to be active. So for example, we can do the Q command to have the monitor program print out its version string. We can, let's say, go to address hex 0010 and read some memory. This is actually going to be the contents of the VIRQ tab table in memory, so that's the contents of that table. So this is all great. The interrupt handler continues to execute. The monitor program continues to execute. This is pretty neat. We can do interesting things as well. For example, we can, if we set the mask register value back to FF, notice the counter stops counting up, and essentially that's because IRQ3 is now blocked by the interrupt controller because we've blocked off that bit in the mask register. And so if I set the mask value back to F7, we should see the count values continuing to count up. In addition, if I run the Q command again, that's going to block interrupts at the processor level. And once again, the interrupt is no longer generated when we block that bit in the condition code register. And so if I run it again, the count starts increasing again. So this is basically complete success. We have IRQ3 being handled. This also, because this is an edge-triggered interrupt generated by our timer counter chip, that also shows that the edge detection logic is working correctly. So basically, interrupts are working. This is awesome. All right, so we were able to get interrupts completely working, so that's very exciting. This was one of the most technically challenging parts of the project so far, so it's very satisfying to have it come to a successful conclusion. In terms of what we're going to be doing next, I have a few things I would like to work on. I am planning to work on a keyboard controller for the Commodore 16 keyboard. I would like to add sound and graphics support to the system, and I've also been thinking about having PCBs fabbed for the modules such as the core module, the peripheral module, and of course our interrupt controller. So I may work on that sometime soon. And in any case, I will see you in the next video.